The James Webb Space Telescope has fundamentally altered our understanding of the cosmos in ways that scientists are still struggling to comprehend. When the first images arrived in July 2022, astronomers around the world sat in stunned silence. What they were seeing shouldn't have been possible. Galaxies that formed just a few 100 million years after the Big Bang appeared not as the small, dim, chaotic structures they expected, but as massive, bright, surprisingly mature systems that challenged everything we thought we knew about cosmic evolution. Let's be clear about what we're dealing with here. The Webb telescope isn't just a better Hubble. It's an entirely different beast. With a mirror over 6 times larger in collecting area and instruments tuned to infrared wavelengths, Webb can peer through cosmic dust and look back to times when the universe was barely out of its infancy. It can analyze the chemical compositions of exoplanet atmospheres, watch stars being born inside dense nebulae, and observe galaxies so distant their light has been traveling toward us for over 13 billion years. But here's where things get interesting. Those early galaxies Webb discovered are causing a crisis in cosmology. According to our standard models, galaxies should form gradually. Small clumps of dark matter would attract ordinary matter, slowly building up over hundreds of millions of years. The first galaxies should be small, irregular, and relatively dim. They should be cosmic teenagers, awkward and still figuring themselves out. Instead, Webb found galaxies that look like they hit the gym, got a degree, and bought a house all within a few 100 million years of the universe's birth. Take galaxy JWST GS-Z 14-0, for example. This galaxy existed when the universe was only 290 million years old. That's 2% of the universe's current age. To put this in perspective, if the universe's entire history were compressed into a single year, this galaxy would have formed by mid-January. And it's not some faint smudge. It's bright, it's massive, containing hundreds of millions of stars, and it shows signs of complex chemistry. Elements heavier than hydrogen and helium, which can only be created inside stars, are already present in abundance. How is this possible? Stars need time to form, live their lives, and die in supernovae to create heavy elements. Multiple generations of stars should be required to build up the chemical complexity we're seeing. But there simply hasn't been enough time. It's like walking into a forest and finding ancient redwood trees when you know for certain that the land was barren just a few years ago. Some astronomers have proposed that these early galaxies formed with extraordinary efficiency, converting almost all their available gas into stars in massive bursts of star formation. Others suggest that perhaps our understanding of star formation itself needs revision. Maybe in the early universe, conditions allowed for the formation of supermassive stars that lived fast and died young, enriching their surroundings with heavy elements in just a few million years rather than billions. Then there are the supermassive black holes. Webb has detected quasars powered by black holes containing millions or even billions of solar masses existing when the universe was less than 1 billion years old. This is deeply problematic. Black holes grow by consuming matter, but there are physical limits to how fast they can eat. Even if a black hole started forming immediately after the Big Bang and consumed matter at the maximum possible rate constantly without pause, it shouldn't be able to reach the masses we're observing in the time available. One galaxy, Source 1019, contains a black hole of about 9 million solar masses when the universe was only 570 million years old. To achieve this mass, either these black holes started much bigger than we thought possible, or they found ways to grow faster than our physics allows, or time itself worked differently in the early universe. None of these options are comfortable for physicists. Some researchers have suggested that supermassive black holes might have formed directly from the collapse of massive clouds of gas in the early universe, bypassing the normal stellar evolution route. These so-called direct collapse black holes could have started with masses of thousands or even hundreds of thousands of suns, giving them a significant head start. But even this doesn't fully explain what Webb is seeing. The telescope has also revealed unexpected structure and organization in these early galaxies. Some show clear evidence of spiral arms, bars, and organized rotation patterns that we associate with mature galaxies billions of years older. It's as if evolution hit the fast-forward button in the early universe. The galaxy MAX 0416 Y2 shows hints of a galactic bar, a structure that forms when a galaxy has settled into gravitational stability and stars have had time to rearrange themselves into coherent patterns. This level of organization appearing so early is like finding a perfectly planned city with infrastructure and highways in a region that was supposed to be wilderness. Moving closer to home, Webb has revolutionized the study of exoplanets and their atmospheres. Before Webb, we could detect exoplanets and measure their basic properties like size, mass, and orbit, but characterizing their atmospheres in detail was extraordinarily difficult. Webb changed that overnight. The telescope observed WASP 96b, a gas giant exoplanet about 1,150 light-years away, and produced the most detailed spectrum of an exoplanet atmosphere ever obtained. The spectrum revealed the unmistakable signature of water vapor, along with evidence of clouds and haze. But what's remarkable isn't just what was detected, it's the precision of the detection. Webb can identify specific molecules based on how they absorb different wavelengths of starlight as the planet passes in front of its star. For the first time, we can truly begin to characterize what these distant worlds are actually like. Webb has detected carbon dioxide in the atmosphere of WASP 39b, making it the first unambiguous detection of this molecule on a planet outside our solar system. It found methane and carbon dioxide on the giant exoplanet K2-18b, which orbits in its star's habitable zone and might have conditions suitable for liquid water beneath a hydrogen-rich atmosphere. This exoplanet, K2-18b, is particularly intriguing because it represents a new class of world that doesn't exist in our solar system. It's larger than Earth but smaller than Neptune, with a mass about 8 times that of Earth. Scientists call these planets mini-Neptunes or sub-Neptunes, and they're incredibly common in our galaxy, yet we have no local example to study. Webb's observations suggest that some of these worlds might be covered by global oceans underneath thick hydrogen atmospheres. These hypothetical planets have been dubbed Hycean worlds, a combination of hydrogen and ocean. The implications are staggering. If Hycean worlds are common, and if they can support liquid water despite their exotic atmospheres, then the number of potentially habitable environments in our galaxy might be far larger than we ever imagined. We've been searching for Earth-like planets orbiting Sun-like stars, but we might have been thinking too narrowly. Life might thrive in oceans beneath hydrogen skies on worlds utterly unlike our own. Webb has also turned its gaze to the ice giants of our own solar system. Images of Neptune revealed the planet's rings with extraordinary clarity, including dusty rings that haven't been seen since Voyager 2 flew past in 1989. More importantly, Webb detected methane ice clouds in Neptune's atmosphere and tracked atmospheric dynamics in unprecedented detail. Similar observations of Uranus revealed its faint rings and moons, providing data that will help us understand these mysterious worlds better. But let's return to those troublesome early galaxies, because the more Webb looks, the stranger things become. The telescope discovered galaxies with redshifts exceeding 10, meaning we're seeing them as they were less than 500 million years after the Big Bang. Some candidates have been identified with redshifts potentially reaching 16 or even higher, pushing back to within 200 million years of the cosmic beginning. What makes this even more perplexing is that these early galaxies don't look like prototypes. They look like they know what they're doing. They have well-defined structures, active star formation, and diverse stellar populations. Some show evidence of dust, which is composed of heavy elements that should take time to produce. The galaxy Glass Z13, confirmed at a redshift of about 13, shows spectroscopic evidence of oxygen, carbon, and nitrogen, elements that in our current understanding require multiple generations of stars to create. Astronomers are now seriously questioning whether our cosmological models need fundamental revision. The standard lambda-CDM model, which has successfully explained the large-scale structure of the universe, the cosmic microwave background radiation, and the expansion history of the cosmos, might be missing something crucial about how galaxies form and evolve. One possibility is that dark matter behaves differently than we thought. If dark matter particles interact with each other more than we assumed, or if they have properties we haven't accounted for, it could lead to faster gravitational collapse and earlier galaxy formation. Another idea suggests that the initial density fluctuations in the early universe were larger than predicted, providing seeds that could grow into galaxies more quickly. Some physicists have even proposed more radical solutions, suggesting that the cosmological constant or dark energy might have evolved over time, or that fundamental physics operated differently in the universe's first billion years. These are uncomfortable propositions because they require us to abandon or significantly modify theories that have been extraordinarily successful at explaining observations. Webb's observations of star formation regions have also yielded surprises. The telescope has peered inside the Carina Nebula, the Tarantula Nebula, and other stellar nurseries, revealing thousands of previously hidden young stars and protostars. These regions are thick with dust that blocks visible light, but infrared radiation passes through, allowing Webb to see the birth of stars in unprecedented detail. In the Tarantula Nebula, located in the Large Magellanic Cloud, Webb discovered protostars that were completely invisible to previous telescopes. The nebula is one of the most active star-forming regions known, and Webb's images revealed the complex interplay between newly formed massive stars and their surrounding environment. The powerful radiation and stellar winds from young massive stars are sculpting the nebula, compressing gas in some regions and triggering new star formation while simultaneously blowing away gas in other areas, potentially preventing stars from forming. What's particularly fascinating is seeing stars at various stages of development all in one place. Webb can identify stars that are still deeply embedded in their natal cocoons of gas and dust, stars that have just begun nuclear fusion in their cores, and slightly older stars that have cleared away their immediate surroundings. This allows astronomers to piece together the timeline of stellar birth with unprecedented precision. The telescope has also observed brown dwarfs, those failed stars that never quite accumulated enough mass to sustain hydrogen fusion. Webb's sensitivity has revealed brown dwarfs with masses barely a dozen times that of Jupiter, blurring the line between planet and star. Some of these objects show evidence of complex atmospheric chemistry, with clouds made of exotic materials like molten iron droplets or minerals that would be solid rocks on Earth. When Webb turned toward the center of our galaxy, it discovered hundreds of new brown dwarfs in the crowded stellar environment near Sagittarius A star, the supermassive black hole at the Milky Way's heart. This region is one of the most extreme environments in our galaxy, with intense radiation fields and strong gravitational forces, yet stars and brown dwarfs persist and even form there. Webb's observations are helping us understand how star formation can occur even in such hostile conditions. Speaking of Sagittarius A star, Webb has provided new insights into the supermassive black hole and its surroundings. While Webb doesn't observe the black hole directly, it can study the stars orbiting nearby and the hot gas being pulled toward the event horizon. One star, designated S2, orbits the black hole with a period of just 16 years, reaching speeds of nearly 3% the speed of light at closest approach. Webb's infrared capabilities allow continuous monitoring of this star and others in the central cluster, providing tests of general relativity in the strongest gravitational field accessible to our observations. The study of distant quasars has also been transformed. Quasars are among the brightest objects in the universe, powered by matter falling into supermassive black holes at the centers of galaxies. As material spirals inward, it heats to millions of degrees and emits tremendous amounts of radiation across the electromagnetic spectrum. Webb can observe the infrared emission from these objects and, crucially, can study the host galaxies surrounding them. For decades, astronomers struggled to observe quasar-host galaxies because the brilliant light from the quasar itself overwhelms the much dimmer galactic light. It's like trying to study a candle while staring at a spotlight. But Webb's sensitivity and image quality allow astronomers to separate the quasar light from the galaxy light, revealing what these host galaxies actually look like. The results have been surprising. Many high-redshift quasars reside in galaxies that appear remarkably normal, without the obvious signs of recent major mergers or disruptions that theorists expected. According to conventional wisdom, a quasar should be triggered when two galaxies collide, funneling large amounts of gas toward the central black hole. But many of Webb's quasar hosts look peaceful and undisturbed, suggesting that black holes can be fed through more subtle processes. Other observations have revealed quasars in the process of merging, with two supermassive black holes in the same system, each producing its own quasar signature. These dual quasars will eventually merge, producing gravitational waves that, if they occurred closer to us, would be detectable by gravitational wave observatories like LIGO. The mergers of supermassive black holes are among the most energetic events possible in the universe, and Webb is giving us our first good looks at these systems before they collide. The telescope has made remarkable discoveries about stellar death as well. Observations of supernova remnants have revealed intricate structures and chemical compositions that challenge our understanding of how massive stars end their lives. Webb observed the remnant of supernova 1987A, the closest supernova observed in modern times, which exploded in the Large Magellanic Cloud in 1987. The observations revealed dense clumps of material in the expanding debris, providing clues about the original star's structure and the physics of the explosion itself. One of the most exciting findings involves the detection of heavy elements in supernova remnants. Webb identified emission lines from ionized argon, sulfur, and other elements, mapping their distribution through the expanding shell. These elements were forged in the star's core and in the supernova explosion itself, and Webb's observations are revealing how they're distributed and mixed as the remnant expands. The telescope has also studied Wolf-Rayet stars, massive stars near the end of their lives that have shed their outer hydrogen layers and are now fusing helium and heavier elements in their cores. These stars drive powerful stellar winds that blow away several Earth masses of material every year. Webb observed WR-140, a Wolf-Rayet star in a binary system, and discovered an extraordinary pattern of nested shells of dust surrounding it. These shells form because the two stars in the system orbit each other, and the Wolf-Rayet star produces more dust when it's closest to its companion. Since the orbit is elliptical, the stars come close together periodically, and each close approach creates a new shell of dust. Webb counted more than 17 of these shells, creating a pattern that looks like tree rings or ripples on a pond. Each shell represents a close approach, and by measuring their spacing, astronomers can reconstruct the orbital history of the system. This discovery matters because dust is crucial to the universe. Dust grains serve as the building blocks of planets and provide the surfaces where molecules can form in space. Understanding where dust comes from and how it's distributed is essential to understanding planet formation and the chemical evolution of galaxies. Wolf-Rayet stars might be significant contributors to cosmic dust, particularly in the early universe when such massive stars would have been more common. Webb's observations of protoplanetary disks around young stars have revealed the birthplaces of planets in exquisite detail. These disks of gas and dust are where planets form, and Webb can see structures within them that hint at planets already taking shape. Gaps and rings in the disk indicate where planets are clearing out material along their orbits. Spiral patterns suggest gravitational disturbances from massive bodies. Bright knots might be clumps of material condensing into planetesimals. The disk around the star HL Tauri, which had been famously imaged by the ALMA radio telescope array, was observed by Webb in infrared light, revealing complementary information about the temperature distribution and the composition of the disk material. The combination of radio and infrared observations provides a three-dimensional view of the disk structure and chemistry. Webb has also detected water vapor in protoplanetary disks, including the inner regions where rocky planets like Earth might form. This is significant because it suggests that water might be delivered to forming planets directly from the disk, rather than requiring later delivery by comets or asteroids. If water is present during planet formation, then potentially habitable worlds might be more common than we thought. The study of our own solar system's outer regions has been enhanced dramatically. Webb observed Jupiter and its moons, revealing auroras at the planet's poles, atmospheric storms in unprecedented detail, and clear images of the faint ring system. But more importantly, Webb studied Jupiter's moon Europa, which harbors a subsurface ocean beneath its icy crust. The observations searched for evidence of water vapor plumes erupting from the surface, similar to those seen on Saturn's moon Enceladus. While the results are still being analyzed, any detection of plumes on Europa would be tremendously significant because it would provide a way to sample the subsurface ocean without drilling through kilometers of ice. If plumes are present and can be studied with future missions, we might be able to determine whether Europa's ocean contains the chemistry necessary for life. Saturn and its rings were imaged with stunning clarity, but what caught astronomers' attention was the extraordinary detail visible in the planet's atmosphere and the structure of the rings themselves. Webb can distinguish between ice particles of different sizes in the rings based on how they reflect infrared light, providing new data about the rings' composition and age. The question of whether Saturn's rings are ancient or relatively young has been debated for years, and Webb's observations are contributing new evidence to this discussion. The telescope observed Titan, Saturn's largest moon, which has a thick nitrogen atmosphere and liquid methane lakes on its surface. Webb's infrared eyes can see through Titan's hazy atmosphere to map surface features and identify clouds in the moon's atmosphere. Titan is the only other world in our solar system with stable liquid on its surface, though instead of water, it's methane and ethane. Understanding Titan's weather, its seasonal changes, and the chemistry occurring in its atmosphere helps us understand prebiotic chemistry and potentially the conditions that existed on Earth before life arose. Webb's observations of distant galaxy clusters have revealed some of the most dramatic examples of gravitational lensing ever recorded. When light from a distant galaxy passes near a massive foreground object like a galaxy cluster, the intense gravity warps spacetime itself, bending the light's path. This effect, predicted by Einstein's general relativity, acts like a cosmic magnifying glass, allowing us to see objects that would otherwise be too faint and distant to detect. The galaxy cluster SMACS 0723, featured in Webb's first deep field image, demonstrates this effect beautifully. The cluster's gravity magnifies and distorts light from galaxies behind it, creating multiple stretched and distorted images of the same background galaxy. Some appear as arcs wrapping around the cluster, while others are smeared into long streaks. By carefully analyzing these distortions, astronomers can map the distribution of matter in the cluster, including the dark matter that makes up most of its mass but emits no light. What's remarkable is that gravitational lensing reveals dark matter's presence with extraordinary precision. The cluster's visible galaxies account for only a small fraction of the total mass needed to produce the observed lensing. The rest is dark matter, and Webb's observations allow astronomers to create detailed maps showing exactly where this invisible matter is located. These maps reveal that dark matter forms a smooth halo surrounding the cluster, with the visible galaxies embedded within it like raisins in bread. But gravitational lensing does more than just map dark matter. It also magnifies distant galaxies, making them appear brighter and larger than they would otherwise. This natural magnification allows Webb to study galaxies that formed in the first few 100 million years after the Big Bang in far greater detail than would otherwise be possible. Without lensing, these galaxies would be tiny, faint smudges barely distinguishable from noise. With lensing, they become analyzable objects with measurable properties. One particularly intriguing discovery involves a galaxy magnified by the cluster MAX 0647, which appears to have been lensed into 3 separate images. Detailed spectroscopic analysis revealed that this galaxy, existing just 420 million years after the Big Bang, contains pockets of intense star formation, creating stars at a rate of about 1 solar mass per year. For comparison, our Milky Way currently forms roughly 2 solar masses worth of stars per year, but this ancient galaxy is much smaller, meaning its star formation is extraordinarily concentrated. The chemical composition of these early galaxies continues to puzzle researchers. Webb spectrographs can identify specific elements by their emission or absorption lines, creating a chemical fingerprint of the galaxy. What we're seeing is that even very early galaxies contain surprisingly high abundances of elements like carbon, oxygen, and nitrogen. These elements are created inside stars through nuclear fusion, then distributed through space when stars die. The presence of these elements in such young galaxies means that star formation, stellar evolution, and stellar death must have occurred very rapidly in the early universe. One proposed explanation involves population 3 stars, a theoretical first generation of stars that has never been directly observed. These stars would have formed from pristine hydrogen and helium gas, without any heavy elements at all. Theory suggests they would have been extremely massive, perhaps hundreds of times the mass of our Sun, burning incredibly hot and bright, and dying in spectacular supernovae after just a few million years. These explosions would have seeded the surrounding gas with the first heavy elements, enabling the formation of the galaxies we see. Webb is actively searching for population 3 stars or their remnants, but none have been definitively identified yet. The challenge is that these stars would have been extremely rare even in the early universe, and they lived such short lives that catching one in the act requires extraordinary luck. However, Webb has identified several candidate galaxies that might contain population 3 stars based on their unusual spectral properties. These candidates show emission patterns consistent with very hot, massive stars and unusually low abundances of heavy elements, exactly what we'd expect if we were seeing a galaxy dominated by first-generation stars. The telescope has also made significant contributions to our understanding of dark energy, the mysterious force causing the universe's expansion to accelerate. By observing Type Ia supernovae in distant galaxies, astronomers can measure cosmic distances with high precision. These supernovae are standardizable candles, meaning we know their intrinsic brightness, so by measuring how bright they appear, we can calculate how far away they are. Webb has observed several Type Ia supernovae in galaxies at various distances, contributing to the cosmic distance ladder that allows us to measure the universe's expansion history. The data suggest that dark energy has been relatively constant over cosmic time, but the measurements also hint at some tension with results from other methods, particularly measurements of the cosmic microwave background by satellites like Planck. This tension might indicate that our cosmological model needs refinement, or it could point to systematic errors in one or more measurement techniques. One of Webb's most scientifically valuable capabilities is its ability to obtain detailed spectra of extremely faint objects. A spectrum spreads out an object's light into its component wavelengths, revealing information about temperature, composition, motion, and physical conditions. For distant galaxies, obtaining spectra was often impossible with previous telescopes because the galaxies were simply too faint. Webb has changed this completely. The telescope spectrographs can collect enough light from very distant, faint galaxies to produce high-quality spectra in just a few hours of observation. These spectra reveal not just the galaxy's redshift and therefore its distance, but also detailed information about what's happening inside. Emission lines from ionized gas indicate regions of active star formation. Absorption lines show what elements are present in the galaxy's stars. The shapes and widths of spectral lines reveal how fast gas is moving, indicating the presence of galactic winds, rotating disks, or mergers. Webb observed a galaxy designated GOODS S45, which showed extremely broad emission lines indicating gas moving at thousands of kilometers per second. This suggests a powerful outflow driven by either intense star formation or an active galactic nucleus. Such outflows can regulate galaxy growth by blowing gas out of the galaxy, preventing it from forming stars. Understanding these feedback processes is crucial to understanding why galaxies stop growing and how they evolve over cosmic time. The study of galaxy mergers has also been revolutionized. When galaxies collide and merge, their shapes become distorted, star formation is often triggered, and their central black holes may become active. Webb can observe mergers at various stages and at various distances, allowing astronomers to understand how the merger process has changed over cosmic history. Some mergers show tidal tails, long streamers of stars pulled out by gravitational forces during the interaction. Others display compressed gas clouds where star formation is occurring at accelerated rates. Still others show double nuclei, two bright central concentrations that represent the cores of the merging galaxies before they've fully coalesced. By studying mergers in the early universe and comparing them to nearby mergers, astronomers can determine how the merger rate has changed over time and how mergers contribute to galaxy growth. Interestingly, Webb's observations suggest that major mergers might be less important for galaxy growth than previously thought, at least in the early universe. Many of the massive early galaxies show no clear signs of recent mergers. Instead, they appear to be growing through steady accretion of gas from their surroundings, forming stars continuously rather than in merger-triggered bursts. This has significant implications for our understanding of how galaxies assemble their mass. The telescope has made unexpected discoveries about the intergalactic medium, the diffuse gas that exists between galaxies. This gas is incredibly tenuous, with densities far lower than the best vacuum achievable in Earth laboratories, yet it contains most of the ordinary matter in the universe. Stars and galaxies, despite being all we can easily see, represent only a small fraction of the universe's normal matter. Most of it exists in this intergalactic gas. Webb has detected this gas indirectly by observing how it absorbs light from background quasars. As a quasar's light travels through space toward us, it passes through clouds of intergalactic gas. Each cloud imprints absorption lines on the spectrum, and by analyzing these lines, astronomers can determine the gas's composition, temperature, and density. What we're learning is that the intergalactic medium is more structured and chemically enriched than expected, even at high redshifts. This enrichment is puzzling because it means that heavy elements produced in stars have somehow been transported out of galaxies and into the intergalactic medium. The most likely mechanism is galactic winds driven by supernovae and active galactic nuclei, which can blow metal-enriched gas out of galaxies at high speeds. Once this gas escapes the galaxy's gravitational pull, it becomes part of the intergalactic medium, gradually mixing and spreading through space. Webb's infrared capabilities have allowed unprecedented studies of dusty star-forming galaxies, a class of objects that are nearly invisible to optical telescopes but extremely luminous in infrared light. These galaxies are forming stars at prodigious rates, sometimes creating hundreds or even thousands of solar masses of stars per year. The intense star formation heat surrounding dust, which then re-radiates the energy as infrared light. Before Webb, studying these galaxies in detail was challenging because even though they're bright in total infrared output, they're often very distant, making them appear faint. Webb's sensitivity has allowed detailed observations, revealing that these dusty starbursts are often triggered by galaxy mergers or interactions. The merger compresses gas, triggering rapid star formation that creates massive stars, which in turn produce copious amounts of dust through stellar winds and supernovae. One particularly remarkable system, SPT 0311-58, consists of two dusty star-forming galaxies in the process of merging when the universe was only 780 million years old. The total star formation rate in this system exceeds 3,000 solar masses per year, and the galaxies contain enormous amounts of dust, far more than should exist at such early times according to standard models. Where did all this dust come from so quickly? The question remains open, but it's clear that dust production was remarkably efficient in the early universe. Webb has also observed submillimeter galaxies, another class of dust-obscured objects identified by their emission at millimeter and submillimeter wavelengths. These galaxies are thought to represent a phase in galaxy evolution when massive galaxies are rapidly building their stellar populations. Webb's infrared observations complement radio and submillimeter observations, providing a complete picture of these objects' properties. What's emerging is a more complex picture of galaxy evolution than we previously had. Galaxies don't simply form stars at a steady rate throughout their lives. Instead, they go through phases of intense activity punctuated by quieter periods. Some galaxies experience multiple starburst episodes, while others form most of their stars early and then fade into quiescence. Understanding what drives these different evolutionary paths is one of the key goals of modern astrophysics. The role of environment in galaxy evolution has also become clearer through Webb's observations. Galaxies in dense environments like galaxy clusters behave differently from isolated galaxies in the field. Cluster galaxies often have their star formation suppressed, a process called quenching, because the hot gas in the cluster strips away their cold gas reservoirs needed for star formation. Webb can observe this process in action by comparing galaxies in different environments at different cosmic epochs. One surprising finding is that environmental quenching appears to have been less efficient in the early universe. High redshift protoclusters, the progenitors of today's massive galaxy clusters, contain galaxies with vigorous star formation. Unlike the red, dead galaxies that dominate clusters today. This suggests that environmental effects on galaxies have strengthened over cosmic time, perhaps as galaxy clusters themselves have evolved and developed hot intracluster gas. Webb's study of planetary nebulae has revealed intricate structures and chemical compositions that inform our understanding of stellar evolution. Planetary nebulae form when low to intermediate mass stars like our Sun reach the end of their lives and eject their outer layers, creating expanding shells of glowing gas. The remaining stellar core becomes a white dwarf, a dense remnant about the size of Earth but containing roughly the mass of the Sun. The Ring Nebula, one of the most famous planetary nebulae, was imaged by Webb in unprecedented detail. The observations revealed the nebula's three-dimensional structure, showing that it's not actually a ring but rather a cylinder or barrel shape viewed from the side. The nebula contains intricate filaments and knots where dense clumps of gas are being illuminated and ionized by ultraviolet radiation from the central white dwarf. Chemical analysis of planetary nebulae tells us what happened inside the star during its lifetime. Elements like carbon, nitrogen, and oxygen were produced through nuclear fusion in the star's interior and then mixed to the surface through convection. When the star ejected its outer layers, these processed elements were released into space, eventually becoming part of the raw material for new stars and planets. In this sense, planetary nebulae are cosmic recyclers, returning enriched material to the interstellar medium. Webb observed the Southern Ring Nebula and discovered that it's actually being shaped by not one but two stars at its center. The primary star, now a white dwarf, ejected the nebula, but a companion star has influenced the nebula's evolution through gravitational interactions and possibly by capturing some of the ejected material. This binary nature explains the nebula's complex, asymmetric structure, which has puzzled astronomers for years. The discovery that many planetary nebulae are shaped by binary interactions is significant because it suggests that stellar companions play a crucial role in the death throes of Sun-like stars. If our Sun had a companion star, our solar system's fate would be quite different when the Sun reaches the end of its life billions of years from now. Webb has also studied white dwarfs themselves, the dense stellar remnants left behind after planetary nebula ejection. White dwarfs are fascinating objects where matter exists in an exotic state. A typical white dwarf has a mass comparable to the Sun compressed into a volume about the size of Earth. This gives it a density of roughly 1,000,000 grams per cubic centimeter, 1,000,000 times denser than water. At such densities, matter becomes electron degenerate, meaning quantum mechanical effects prevent further compression. Some white dwarfs show evidence of heavy element pollution in their atmospheres, indicating that they've recently accreted material, likely from asteroids or comets that wandered too close. By studying the composition of this accreted material, astronomers can learn about the composition of planetary systems around other stars. It's an indirect way of studying extrasolar asteroids and comets, which are too small and faint to observe directly. Webb observed several white dwarfs with infrared excesses, indicating they're surrounded by dusty debris disks. These disks form from the tidal disruption of asteroids that passed within the white dwarf's Roche limit, the distance at which tidal forces overcome the asteroid's self-gravity. The shredded asteroid material forms a disk that gradually accretes onto the white dwarf, polluting its atmosphere with heavy elements. The study of cool subdwarf stars has also benefited from Webb's capabilities. These are ancient, metal-poor stars that formed early in our galaxy's history. They have very low abundances of elements heavier than helium because they formed from gas that had been minimally enriched by previous stellar generations. Studying these stars provides insights into the early Milky Way and the first few billion years of our galaxy's evolution. Webb's infrared sensitivity is particularly valuable for studying the coolest and faintest of these ancient stars, objects that are barely visible to optical telescopes. By obtaining spectra of these stars, astronomers can measure their detailed chemical compositions, revealing exactly which elements were present in the gas from which they formed. This chemical archaeology allows us to reconstruct the history of nucleosynthesis and chemical enrichment in our galaxy. One fascinating discovery involves hypervelocity stars, objects moving so fast they'll eventually escape the Milky Way's gravity entirely. These stars were likely accelerated to their extreme velocities through close encounters with the supermassive black hole at our galaxy's center or through supernova explosions in binary systems. Webb has observed several hypervelocity stars and measured their properties, helping to constrain the mechanisms that can accelerate stars to such high speeds. The infrared view has also enhanced our understanding of stellar populations in nearby galaxies. By observing galaxies in the local group, the small collection of galaxies that includes the Milky Way, Andromeda, and several dozen smaller galaxies, Webb can resolve individual stars and study their properties in detail. This allows detailed comparisons between stellar populations in different galaxies, revealing how star formation history varies from galaxy to galaxy. The Large Magellanic Cloud and Small Magellanic Cloud, two dwarf galaxies orbiting the Milky Way, have been observed extensively. These galaxies have lower metallicities than the Milky Way, meaning they contain fewer heavy elements, and their star formation histories differ significantly. Webb's observations are helping astronomers understand why these differences exist and what they tell us about galaxy evolution in general. One key question is whether dwarf galaxies are simply scaled-down versions of larger galaxies or whether they follow fundamentally different evolutionary paths. Webb's detailed observations of stellar populations, star clusters, and star-forming regions in dwarf galaxies are providing answers. What's emerging is that dwarf galaxies are indeed different, not just smaller. They're more susceptible to having their gas reservoirs stripped away by interactions with larger galaxies, and their shallow gravitational potential wells mean that supernova explosions can blow gas out more easily, sometimes halting star formation entirely for extended periods. The study of globular clusters, dense spherical collections of hundreds of thousands to millions of stars, has also been enhanced. These ancient star clusters formed early in galactic history and contain some of the oldest stars in the universe. Webb can observe globular clusters in nearby galaxies, resolving individual stars even in relatively distant systems. This allows age dating of stellar populations and reconstruction of star formation histories. Interestingly, Webb has found evidence that globular cluster formation might still be occurring in some environments. While most globular clusters are ancient, some young massive clusters have been identified in interacting galaxies where intense star formation is occurring. These young clusters might be modern analogues of ancient globular clusters, allowing us to study the formation process directly rather than trying to infer it from ancient systems. The cores of globular clusters are particularly interesting because stellar densities there are extraordinarily high. Stars are packed so closely that interactions between them are common. These interactions can form exotic objects like blue stragglers, stars that appear younger than they should because they've gained mass from a companion, or millisecond pulsars, rapidly rotating neutron stars spun up by accretion from a companion star. Webb's high-resolution infrared imaging allows detailed studies of globular cluster cores, revealing these exotic populations. Webb has revolutionized our ability to study the atmospheres of hot Jupiters, a class of exoplanets that orbit extremely close to their host stars. These planets are tidally locked, meaning the same hemisphere always faces the star, just as the same side of the Moon always faces Earth. This creates extreme temperature differences between the day side and night side, driving powerful atmospheric winds that redistribute heat around the planet. The exoplanet WASP-121b, often called a hot Jupiter on steroids, orbits so close to its star that its dayside temperature exceeds 3000 Kelvin, hot enough to vaporize most metals. Webb's observations detected gaseous iron and magnesium in the planet's atmosphere, elements that would be solid at Earth's temperature but exist as vapor in WASP-121b's inferno. More remarkably, Webb mapped the temperature distribution across the planet's surface, revealing that the hottest region isn't directly under the star but shifted eastward by the planet's fierce atmospheric winds. These wind patterns tell us about atmospheric dynamics on alien worlds. The winds on WASP-121b reach speeds of several kilometers per second, far faster than any hurricane on Earth. Understanding these atmospheric circulation patterns helps us predict what other hot Jupiter atmospheres might be like and provides tests for atmospheric models that can be applied to cooler, potentially habitable planets. Webb observed WASP-18b and detected evidence of quartz clouds in its atmosphere. Quartz, silicon dioxide, is better known on Earth as sand. On WASP-18b, temperatures are high enough that silicon dioxide can exist as vapor, which then condenses into tiny crystalline particles forming clouds. These aren't fluffy water vapor clouds like on Earth but rather mineral clouds composed of tiny gemstones. When light passes through these clouds, it creates unique spectral signatures that Webb can detect. The discovery of exotic cloud compositions has significant implications for understanding planetary atmospheres across the full range of conditions. Clouds affect a planet's energy balance, its appearance, and its spectrum. Being able to identify what clouds are made of allows us to understand atmospheric chemistry and temperature profiles in detail. This knowledge will be crucial when we eventually observe smaller, cooler planets where conditions might be more conducive to life. Webb has also studied ultra-hot Jupiters, planets even more extreme than typical hot Jupiters, with dayside temperatures exceeding 4000 Kelvin. At these temperatures, molecules dissociate into individual atoms. Instead of water vapor or carbon monoxide molecules, we find atomic hydrogen, oxygen, and carbon. The atmospheres of these worlds provide laboratories for studying matter under conditions we can't easily replicate on Earth. One ultra-hot Jupiter, KLT-9b, has a dayside temperature around 4600 Kelvin, making it hotter than many stars. Webb detected atomic iron and titanium in its atmosphere and found that these heavy metals are being blown off the planet by the intense stellar radiation. The planet is essentially evaporating, losing mass to space at a measurable rate. Over billions of years, a significant fraction of the planet's atmosphere could be stripped away, potentially revealing a rocky core underneath or leaving behind a completely different type of world. The study of planet migration has also been informed by Webb's observations. Many hot Jupiters couldn't have formed in their current locations because temperatures so close to their stars would have prevented gas accretion during the planet formation process. Instead, these giants must have formed farther out where conditions were cooler and then migrated inward over time. But the migration mechanism has been debated. Do planets spiral inward through interactions with the protoplanetary disk while it's still present? Or do gravitational interactions with other planets scatter them into eccentric orbits that then circularize through tidal interactions with the star? Webb's observations of young planetary systems are providing clues. By studying protoplanetary disks around young stars and looking for gaps and asymmetries that indicate planetary migration in progress, astronomers can catch the process in action. Some disks show spiral patterns consistent with a massive planet migrating through the disk and creating density waves. Others show gaps at various distances, suggesting multiple planets that might interact gravitationally in the future. The system PDS-70 is particularly remarkable because it contains 2 confirmed planets still forming within their protoplanetary disk. Webb observed this system and detected warm dust in the regions where the planets orbit, along with evidence of gas accretion onto the planets themselves. This is planet formation happening in real time, allowing us to test theoretical models against actual observations. What makes PDS-70 even more interesting is that the inner planet, PDS-70b, appears to have its own circumplanetary disk, a miniature disk of material orbiting the planet. This is significant because circumplanetary disks are thought to be where moons form. Jupiter's major satellites, the Galilean moons, likely formed in a circumplanetary disk billions of years ago. Observing one around PDS-70b gives us a window into how moon systems form around giant planets. Webb's observations of asteroid belt analogues around other stars have revealed systems in various stages of evolution. Some young stars have massive asteroid belts containing far more material than our solar system's asteroid belt. Others have belts that are being cleared out by forming planets. Still others show evidence of recent collisions, with fresh dust being produced by asteroidal impacts. The star Fomalhaut has been studied extensively because it's surrounded by multiple debris belts. Webb's observations revealed the intricate structure of these belts with unprecedented clarity. The main belt, already known from previous observations, appears as a narrow ring. But Webb also detected an inner belt and hints of an even more distant outer belt. The presence of multiple belts suggests multiple planets, with each belt corresponding to a region where planetesimals survived rather than being incorporated into planets or ejected from the system. The asteroid belts around other stars tell us about the violent histories of planetary systems. Debris belts are generated by collisions between asteroids and comets, and the amount of dust present indicates how frequent these collisions are. Young systems have more dust because they still contain numerous small bodies that haven't yet been cleared out. Older systems have less dust because most collisions have already happened. By surveying debris belts around stars of different ages, we can understand how planetary systems evolve and clean themselves up over time. Webb observed the debris disk around Beta Pictoris, one of the nearest and brightest debris disks known. Previous observations had revealed that this disk is viewed nearly edge-on, appearing as a thin line when seen from Earth. Webb's infrared observations detected warm dust very close to the star, within the orbit of the known planet Beta Pictoris b. This warm dust might be produced by comets being perturbed inward by the planet's gravity and then evaporating as they approach the star. Comets around other stars are difficult to observe directly because they're so small and faint, but we can detect them indirectly through the dust and gas they release. When comets evaporate, they produce characteristic emission features from molecules like carbon monoxide, water, and various organic compounds. Webb has detected these signatures in several young planetary systems, providing evidence that comets are common around other stars just as they are in our solar system. The study of organic molecules in space has been transformed by Webb's capabilities. Organic molecules, compounds based on carbon chemistry, are found throughout the universe, not just on Earth. They form in interstellar clouds, in the atmospheres of cool stars, in protoplanetary disks, and on the surfaces of asteroids and comets. Understanding where and how these molecules form is crucial to understanding the origins of life. Webb detected complex organic molecules in the Orion Nebula, including methanol, dimethyl ether, and other carbon-bearing compounds. These molecules form on the surfaces of dust grains in cold molecular clouds. When young stars heat their surroundings, these molecules evaporate from the grain surfaces and can be detected spectroscopically. The inventory of organic molecules in star-forming regions tells us what raw materials are available for incorporation into forming planets. Polycyclic aromatic hydrocarbons, or PAHs, are a particularly important class of organic molecules. These are ring-shaped molecules composed of carbon and hydrogen, and they're ubiquitous in space. PAHs are thought to form in the outflows from dying stars and in regions of intense ultraviolet radiation. They're remarkably stable and can survive harsh conditions. On Earth, PAHs are produced by combustion and are considered pollutants, but in space they're fundamental components of the interstellar medium. Webb has detected PAHs in numerous environments, from nearby star-forming regions to distant galaxies. The specific PAH emission features in a spectrum tell us about temperature, radiation field intensity, and ionization state. This makes PAHs valuable diagnostic tools for understanding conditions in regions we can't observe directly. In distant galaxies, PAH emission can trace star formation and indicate how intensely stars are radiating. One of the great unsolved questions in astrobiology is how the complex organic molecules necessary for life arose. Did they form on Earth through chemical reactions in the primordial ocean and atmosphere? Or were they delivered from space by comets and asteroids? Webb's observations of organic chemistry in space support the idea that at least some prebiotic molecules could have been delivered from space. If the building blocks of life are common throughout the universe, then life itself might be common as well. The telescope observed several molecular clouds where stars haven't yet begun forming. These dark clouds are among the coldest places in the universe, with temperatures just a few degrees above absolute zero. At these temperatures, most molecules freeze onto dust grains, forming icy mantles. Webb's infrared observations can detect these ices by their absorption features when background starlight passes through the cloud. The ice mantles on dust grains contain water ice, as expected, but also frozen carbon monoxide, carbon dioxide, methane, ammonia, and more complex molecules. When new stars eventually form within these clouds, the heat will vaporize these ices, releasing the molecules into the gas phase where they can participate in chemical reactions. Some of these molecules will be incorporated into forming planets and comets, potentially delivering organic material to planetary surfaces. Webb discovered ices containing frozen carbon dioxide and methanol in several dark clouds. Methanol is particularly interesting because it's a relatively complex organic molecule that can serve as a starting point for building even more complex molecules. The presence of methanol ice in molecular clouds suggests that organic chemistry is already occurring even before stars and planets form. The study of isotopes has also been advanced by Webb's spectroscopic capabilities. Isotopes are variants of elements with different numbers of neutrons. For example, normal carbon has 6 protons and 6 neutrons, but carbon-13 has an extra neutron. The ratios of different isotopes carry information about nuclear processes and chemical reactions. Webb can measure isotope ratios in exoplanet atmospheres, protoplanetary disks, and distant galaxies. In our solar system, different bodies have different isotope ratios, and these differences tell us about their origins and histories. Comets from the Oort cloud have different water isotope ratios than asteroids from the main belt, indicating they formed in different parts of the solar system. By measuring isotope ratios in exoplanetary systems, we can potentially determine where planets formed and whether they migrated. Webb observed the exoplanet WASP-107b and attempted to measure carbon isotope ratios in its atmosphere. While the measurements are challenging and require very high signal-to-noise spectra, preliminary results suggest that carbon-13 is present in detectable amounts. If isotope ratios can be measured reliably in exoplanet atmospheres, it will open an entirely new dimension of planetary characterization. The telescope has also contributed to our understanding of cosmic rays, high-energy particles that bombard Earth from space. While cosmic rays themselves don't emit light, Webb can detect, their interactions with interstellar gas do produce emission that Webb can observe. When cosmic rays collide with hydrogen atoms, they can produce excited states that emit characteristic infrared radiation. By mapping this emission, astronomers can trace cosmic ray distributions through galaxies. Cosmic rays are thought to be accelerated in supernova shock waves and possibly in active galactic nuclei. They play an important role in regulating star formation because they ionize gas, affecting its thermal and chemical properties. In regions with high cosmic ray densities, the ionization can prevent gas clouds from collapsing to form stars. Conversely, in regions with low cosmic ray densities, star formation can proceed more efficiently. Webb observed the supernova remnant Cassiopeia A and detected emission consistent with cosmic ray acceleration at the expanding shock front. This provides direct evidence that supernova remnants are indeed cosmic ray factories, as theory predicts. The observations also revealed unexpected asymmetries in the remnant, suggesting that the original supernova explosion was asymmetric, with more material ejected in some directions than others. These asymmetric explosions are common in supernovae, and understanding why they occur is crucial for understanding stellar evolution and nucleosynthesis. If a supernova explosion is spherically symmetric, the neutron star or black hole left behind should remain at rest at the center of the expanding remnant. But if the explosion is asymmetric, the recoil can give the stellar remnant a kick, sending it flying through space at high velocity. Observations of neutron stars show that many are indeed moving at high velocities, hundreds of kilometers per second or more, confirming that asymmetric explosions are the norm rather than the exception. Webb's observations of supernova remnants are helping us understand what causes these asymmetries. Possibilities include rotation of the progenitor star, binary interactions, or instabilities in the explosion mechanism itself. The study of stellar winds has also benefited from Webb's capabilities. Massive stars drive powerful winds that carry away significant amounts of mass over their lifetimes. These winds enrich the interstellar medium with heavy elements and can trigger star formation in surrounding gas clouds by compressing them. Webb can observe the infrared emission from dust grains condensing in stellar winds, providing information about mass loss rates and wind compositions. One class of stars, luminous blue variables, exhibits particularly extreme mass loss through episodic eruptions. These stars are among the most massive and luminous in the universe, and they're unstable, occasionally ejecting large amounts of material in outburst events. The star Eta Carinae experienced a giant eruption in the 1840s that ejected several solar masses of material, and Webb has observed the ejected nebula in detail. The homunculus nebula surrounding Eta Carinae shows a bipolar structure with lobes of material expanding in opposite directions. Webb's observations revealed the temperature and composition distribution through the nebula and detected dust grains that condensed from the ejected gas. These observations help us understand not only Eta Carinae specifically but also the general phenomenon of eruptive mass loss in very massive stars. Such eruptive mass loss might be crucial for determining the final fates of the most massive stars. Stars above about 150 solar masses are thought to be unstable due to a process called the pair instability, where gamma rays in the star's core become energetic enough to spontaneously create electron-positron pairs. This removes pressure support, causing the core to collapse, which triggers runaway thermonuclear burning. The result could be a complete disruption of the star without leaving a remnant, or a series of violent pulses that eject most of the star's mass before it finally collapses. Webb is searching for evidence of pair instability supernovae in the distant universe where such extremely massive stars should have been more common. Identifying these events would confirm theoretical predictions and help us understand the maximum masses that stars can achieve. So far, no definitive pair instability supernovae have been identified, but several candidates are being studied. The telescope has observed magnetars, neutron stars with extraordinarily powerful magnetic fields, thousands of trillions of times stronger than Earth's magnetic field. These objects occasionally produce bursts of X-rays and gamma rays, and Webb can observe the infrared emission from dust heated by these outbursts. While magnetars themselves don't emit much infrared radiation, their energetic outbursts can heat surrounding material, creating transient infrared sources. One magnetar, SGR 1806-20, produced a giant flare in 2004 that was detected across the electromagnetic spectrum. Webb has observed the remnant of this flare, looking for any long-lasting infrared emission or changes in the surrounding environment. Understanding magnetar flares is important because they're among the most energetic events known, briefly outshining entire galaxies in high-energy radiation. Webb's observations of galaxy evolution have revealed that the peak era of star formation in the universe occurred roughly 10 billion years ago, when the universe was about a quarter of its current age. At that time, galaxies were forming stars at rates several times higher than today. Since then, the cosmic star formation rate has been declining. Understanding why star formation has slowed is one of the key questions in cosmology. Several factors contribute to the decline in star formation. Galaxies have consumed much of their gas, converting it into stars. Active galactic nuclei and stellar feedback have heated and expelled gas from galaxies, making it unavailable for star formation. The universe's expansion has slowed the rate at which fresh gas can fall into galaxies from the intergalactic medium. Dark energy's influence has grown over time, accelerating cosmic expansion and making it harder for matter to gravitationally collapse into new structures. Webb has observed galaxies at the peak epoch of star formation and compared them to local galaxies, revealing how galaxy properties have changed over cosmic time. High-redshift star-forming galaxies tend to be more irregular and gas-rich than local galaxies. They often show evidence of recent mergers or interactions. Their central black holes are more actively accreting. These observations paint a picture of a younger, more violent universe where galaxies were still assembling through dramatic events. The transition from star-forming to quiescent galaxies is particularly interesting. Some galaxies stopped forming stars billions of years ago and have remained quiescent since, while others had their star formation quenched more recently. Webb can identify quenched galaxies at various redshifts and study what triggered their shutdown. Was it a major merger that consumed all available gas? Was it feedback from an active galactic nucleus that heated and expelled gas? Or was it environmental effects, such as ram pressure stripping in galaxy clusters? One remarkable finding is that some massive quiescent galaxies already existed when the universe was only 3 billion years old. These galaxies must have formed their stars extremely early and then shut down star formation rapidly. The speed of this evolution is challenging to explain with standard models, adding to the list of surprises Webb has delivered about the early universe. The structure of galaxies has also evolved over cosmic time. Local massive galaxies tend to have large bulges and relatively small disks, while high redshift star-forming galaxies often have the opposite, with large disks and small or absent bulges. This suggests that bulges grow over time, possibly through mergers and the inward migration of stars. Webb's high-resolution imaging allows detailed morphological studies of distant galaxies, revealing how structure develops. Some galaxies at high redshift show clumpy morphologies, with star formation concentrated in several bright regions distributed through the disk rather than in a smooth distribution. These clumps might be giant star-forming complexes much larger than anything in local galaxies, or they might be small satellite galaxies in the process of merging with the main galaxy. Understanding the nature of these clumps helps us understand how galaxies build their mass. Webb has observed cosmic noon, the period around 10 billion years ago when the universe was most active. During this era, galaxy mergers were common, supermassive black holes were growing rapidly, and star formation was at its peak. Studying this epoch is like studying a city during rush hour, when everything is happening simultaneously and interactions between different components are most important. The relationship between black hole growth and galaxy growth during cosmic noon is particularly interesting. Observations show that the masses of supermassive black holes correlate with the masses of their host galaxy bulges. This suggests some kind of coevolution, where black hole growth and galaxy growth regulate each other. When a black hole accretes vigorously, it produces powerful radiation and outflows that can heat gas and prevent star formation. Conversely, when a galaxy undergoes a merger, gas is funneled toward the center, feeding the black hole. Webb has observed this interplay in action. Some galaxies show both vigorous star formation and active galactic nucleus activity simultaneously. Others show evidence that the active galactic nucleus has recently shut down star formation, with young stars present but no ongoing star formation. Still others show star formation occurring but the central black hole is quiescent. These different states represent different phases in the coevolution of galaxies and their black holes. The observations also reveal that not all galaxies follow the same evolutionary path. Some massive galaxies appear to have grown primarily through in situ star formation, converting their own gas into stars over billions of years. Others grew primarily through mergers, assimilating smaller galaxies. Still others used both mechanisms. Understanding which path dominates for different types of galaxies helps us understand the diversity we see in the galaxy population today. Webb's deep field observations have pushed the frontier of observable universe to unprecedented distances. The telescope has detected galaxies with redshifts exceeding 14, meaning we're seeing them as they existed just 200 million years after the Big Bang. At such early times, the universe was only about 1.5% of its current age. These galaxies are among the first generation of luminous structures to form after the cosmic dark ages, the period when the universe had cooled from the Big Bang but stars had not yet ignited. The cosmic dark ages lasted from about 380,000 years after the Big Bang, when the cosmic microwave background radiation was released, until the first stars formed perhaps 100 to 200 million years later. During this period, the universe was filled with neutral hydrogen gas gradually collapsing under gravity to form the first structures. When the first stars finally ignited, their ultraviolet radiation began reionizing the surrounding hydrogen, creating bubbles of ionized gas that gradually expanded and merged. Webb is observing the tail end of the reionization epoch, when these bubbles were merging and the universe was transitioning from mostly neutral to mostly ionized. By studying the spectra of high redshift galaxies and quasars, astronomers can measure how much neutral hydrogen lies between us and these distant objects. The amount of neutral hydrogen has been decreasing over cosmic time as reionization progressed, and Webb's observations are mapping this process in detail. The sources responsible for reionization have been debated for decades. Were they primarily massive stars in early galaxies? Or were they quasars powered by accreting black holes? Webb's observations suggest that galaxies were the dominant contributors, with quasars playing a secondary role. The number density of faint galaxies appears to be high enough to produce the required ionizing photons, whereas quasars, while individually powerful, weren't numerous enough to reionize the entire universe. Understanding reionization matters because it represents one of the major phase transitions in cosmic history. Before reionization, the universe was opaque to ultraviolet light, absorbed by neutral hydrogen. After reionization, the universe became transparent, allowing light to travel freely across cosmic distances. This transformation fundamentally changed the universe's appearance and enabled the formation of more complex structures. Webb has also contributed to studies of the cosmic web, the large-scale structure of the universe. On the largest scales, matter in the universe is distributed in a network of filaments and sheets surrounding vast voids. Galaxies form at the intersections of filaments and within the densest regions. This structure arose from tiny density fluctuations in the early universe that were amplified by gravity over billions of years. By mapping the three-dimensional distribution of galaxies at different cosmic epochs, astronomers can watch the cosmic web evolve. Webb spectroscopic surveys provide redshifts for thousands of galaxies, allowing their positions in three-dimensional space to be determined. This reveals how structure has grown over time and provides tests of cosmological models. One surprising finding is that large-scale structure appears to have developed earlier than expected. Massive galaxy clusters and protoclusters have been identified at high redshifts, indicating that dense regions were already forming when the universe was young. This early structure formation adds to the list of tensions between observations and theoretical predictions, suggesting our cosmological models might need refinement. The Nobel Prize in Physics in 2011 was awarded for the discovery that the universe's expansion is accelerating, driven by dark energy. This acceleration was detected by observing distant Type Ia supernovae and finding they were fainter than expected, indicating greater distances than predicted by a decelerating universe. Webb's observations of supernovae at even greater distances are refining our measurements of dark energy's properties and testing whether it has remained constant over cosmic time. Current evidence suggests that dark energy behaves like Einstein's cosmological constant, a constant energy density pervading all of space. However, alternative models propose that dark energy might evolve over time or have spatial variations. Distinguishing between these possibilities requires precise measurements of cosmic expansion at different epochs, exactly what Webb's supernova observations provide. The ultimate fate of the universe depends on dark energy's nature. If dark energy remains constant, the universe will continue expanding forever, with galaxies outside our local group eventually receding beyond our observable horizon. Star formation will gradually cease as gas is consumed, and eventually, even the longest-lived stars will burn out, leaving a cold, dark universe of dead stellar remnants. This scenario, often called the heat death of the universe, will unfold over trillions of years. Alternatively, if dark energy strengthens over time, the universe could end in a big rip, where accelerating expansion eventually becomes so strong that it tears apart galaxies, stars, planets, and eventually even atoms. Conversely, if dark energy weakens or reverses, the universe might eventually stop expanding and begin contracting, ending in a big crunch where everything collapses back into a singularity. Webb's observations contribute to determining which fate awaits us, though on timescales far beyond human relevance. What matters more immediately is that these observations are revealing the fundamental nature of the universe and our place within it. We live in an expanding universe dominated by mysterious dark matter and dark energy, populated by hundreds of billions of galaxies each containing hundreds of billions of stars, many of those stars hosting planets, and possibly, on some of those planets, other forms of life looking up at their own skies and wondering the same questions we are. The James Webb Space Telescope has given us unprecedented views of this cosmos. It has revealed that galaxy formation occurred earlier and more efficiently than we expected. It has shown us exoplanet atmospheres in chemical detail. It has mapped star formation in nearby nebulae and distant galaxies. It has detected organic molecules throughout space. It has pushed back the observational frontier to the earliest epochs of cosmic history. And it has raised as many questions as it has answered, revealing that the universe is even stranger and more wonderful than we imagined. Every image, every spectrum, every data point returned by Webb represents our species reaching out to understand the universe that created us. The atoms in our bodies were forged in stars, the elements were created in nuclear furnaces billions of years ago and scattered through space by supernova explosions. We are, quite literally, made of stardust, and Webb is showing us the processes that created everything we are and everything around us. As Webb continues its mission over the coming years, it will make discoveries we can't yet predict. It will observe phenomena we haven't imagined. It will challenge our understanding and force us to revise our theories. This is how science progresses, through observation, hypothesis, testing, and revision. Webb is our most powerful tool for observing the universe at infrared wavelengths, and it's showing us a cosmos more complex, more dynamic, and more beautiful than we ever anticipated. The discoveries are just beginning, and the next chapter in our understanding of the universe is being written right now, one observation at a time, as this remarkable telescope continues to peer into the depths of space and time.